to the next participant. It's a team, Creative Quantum AI. Are you there?
Yes, I am here.
How nice. So you can just go ahead.
All right, let me try to share my screen. All right, you should see it now.
Yes, we do.
Do you? Great. Okay, my name is Hannah and I'm a coding concept artist based in Berlin. And I'm very happy to present you the status of our quantum machine learning project. First of all, I would like to mention my very lovable, adorable, smart, and curious, fearless teammates. So there's Grishma, she's from India, and she is a mathematician and a data scientist. And just like myself, she's a real quantum computation addict. And then we got Michael, Dr. Michael Streuwig. He is also a coding artist, actually, and living in Berlin, just like me, but we never met before. So that's really nice. Also, we got Gertjan Akeboom, who is a crypto artist and a Blender 3D artist. All right, so let's go into it. 30 seconds, quantum computation intro. Like those things here, those are qubits. So instead of classical bits where you only have 1 and 0 for computation, you have qubits with the whole phase space. So in principle, there are endless states one qubit can have. And because they are real quantum physical objects, they also bring the option to use those weird quantum phenomena like superposition, entanglement, quantum interferences, and stuff like that, enabling us to teleport, Grover search, and do all kinds of futuristic, nicely weird stuff. Here you can also see a quantum circuit. It's in the right lower corner. That is pretty much the quantum version of an algorithm in classical computation. And what you see at the end, after those gates, those are measurements. And that's something you will find in pretty much all quantum circuits. And when you measure the qubit, no matter what state it was before, it will have only the states 0 or 1. So the wave function you used before will collapse. And that's a very neat feature. And also great for machine learning, as it turns out. Neural networks, here we go. So we got hybrid, quantum, classical, all the machine learning networks we would like to implement within a framing model that is going via reinforcement learning and aiming to optimize the curiosity, the novelty, and also data it collects about the participation. So if you, for example, look at one pattern longer as on another one, this could be used as data the model is using to see how successful it was. So there is this really, really, really beautiful paper I would like to recommend all of you. AI gas, as I call it, I don't know. Maybe it's also AI GAs. And let's take a really quick look into it, maybe. So that's the paper, and this guy, Jeff Kloon, also very inspirational and yeah, great member of the machine learning community. Contributed this not too long ago and is tackling the question of general artificial intelligence and is offering some other path to look into it. So alternative to the manual part we are currently focusing on in the community. Also, there are those self-organizing cellular neural networks that are in a related research team. And you can see this till thread. I would also highly like to recommend, where you find an overview of different versions of this principle. And this is all for classical computation, so our model will have a quantum enhanced version of that. Also, we are inspired by the Wolfram Physics project, of course, because many of you might know that for all kinds of cellular automata, he's like the godfather, and his physics project is also very interesting to look into. I would like to. So that's that. This is an overview of our workflow. So as you can see, the whole project is modular. And on the hardware side of things, we use the superconducting quantum computers that are provided by IBM. They are free to use and you can access them through the cloud. Locally, we are, of course, going CUDA. So we have GPU and TPU enabled PyTorch models. Then our pipeline also got a Blender 3D section where those outputs in the 3D realm are getting designed and optimized at the moment. So we also have the option to do 2Ds or audio or 4D higher dimensional objects that are projected in some way within this playground, I would like to call it. So this whole experiment is open to installations that are reality specific and site specific, from VR, AR, MR, RR, or as you might call real reality. There are a lot of options, and we would like to do some minimal implementation. So we are going to do one on location, physical translation of our pattern generator and VR. All right, so actually I wanted to show you one of our cellular automata models I call Schrödinger's game of life. Many of you might know the Conway's game of life, where you have, this lower section here, traditionally 2D, but you also can have 3D or other dimensional representations of rules that are followed by living and dead cells. And in the Schrödinger picture, we also can use superposition and have Schrödinger cells that are alive and dead at the same time. Also, we can do all kinds of entanglements backwards and forwards through time. So we can do stuff like entangling one generation with a generation that is coming maybe 10 generations after that, and then we will get in the next generation some superposition of those two generations. And I got, because we didn't quite finish right yet, to implement the VR version of this Schrödinger's game of life, but I can show you something instead a little bit, at least. So here we got our test living cell, and the idea is that you can interactively decide where the living cells are starting. Also, you can use the real randomness of the universe accessed through the quantum computers to do some random versions to start with, for example. So this is the first living cell, ta-da. Also, what we got here. This is our test for how heavy it can get in terms of computation, so it can still run in your browser without your internet to collapse. You see already a pretty heavy object. So I think our pipeline is going to be pretty powerful. It looks like it. This is the first test of changing colors for objects. And this is the physics part, stuff down. So at the moment, we are doing all kinds of tests to see what we can do with this framework, and finding the nicest patterns to start with. All right, so here you can also see another implementation of the 3D version of the classical game of life, though that's not quite quantum yet. And that's that. Ta-da, I'm done.
Thank you so much. I'm sure there will be some comments or questions on that. Okay. So, Barry wants to say something.
So, I love the idea with quantum. I have some questions. So, what are you doing on a real data source, right? You feed in some live data. What are you doing to reduce your grid size in order to create the quantum circuit?
The nice thing is that we don't need to focus on that, because when you go cellular, and by the way, like cellular automata, the quantum version of it was also the very first idea of what a quantum computer should be or should do. And this is processing highly in parallel, and also only on spot. So you don't have to do a lot of computation for things that are not within the generation you are computing right now. And you don't need a lot of data to memorize or to access, because every cell has its own little memory. So it only has to look for its rule and its neighbors. And the computation is therefore really a lightweight.
Yeah, cool. That makes sense. And how about, so Schrodinger's equation, how does that tie into the quantum computing simulator when the basis state and the quantum input is already known?
One more time, I didn't get the
So
question.
the Schrodinger's equation, I'm trying to
Yeah.
tie that in, and the basis
Yeah.
state is already known. And so how does the Schrodinger's equation tie into your
If
use
the
case?
state is known, it's not the Schrödinger picture. So in the
Yeah,
Schrödinger
exactly.
picture, you have a superposition. Does this answer your question? I'm not sure. You can
I'm
put
just
a
saying with
qubit.
most like in most cases the input is known. So I feed data in and the basis state is known. And so I don't have to do the Schrödinger. So I'm wondering how this ties into a machine learning problem.
Okay, so the nice thing about superpositions is that you can process two versions of the same mathematical operation in parallel and just get the right solution back afterwards. So this is called the Oracle circuit, and it's very useful to search large data sets, for example, or to do all kinds of stuff where you want to do more than one option in parallel. And it doesn't mean that you only need to use the one state and the zero state the qubit has in its superposition of states, because you can also just switch. You can turn it around. So if you like to have two ones, for example, at the same time, but in different combinations. So one is, for example, entangled with another one that is in a zero state, let's say, and then the next one is entangled with one in the one state, then you will get with one qubit operation two qubit processes computed. Does this make sense?
Yes, it makes absolute sense.
Cool.
And
It's
where I'm
it's
getting
all
at-
pretty weird. Yeah.
No, yeah, I get it. This is my area of focus is quantum machine learning, actually.
Oh yeah.
And so, yeah, so the feedback I would give overall is I know in my cases it's very hard to make a product with quantum. So just focus and try to make one thing work and build a presentation out of that.
Yeah,
And I am
yeah.
very interested in what you guys come up with because I'm
Yeah, it's not the
fascinated by this
first
topic.
rodeo, so we already got some working models
Yeah,
that are
very cool.
good to go. But we are not, yeah, we are pretty ambitious. So it's not just a quantum gun or not just variational eigensolver or stuff, but really a framework where you have a teacher gun that is AI generating within quantum structure.
Nice.
That's the goal. Let's see. Maybe we end up with just a stupid old quantum gun, but I don't think so.
All right. Michelle, is your hand still up from the last presentation, or do you want to say something too?
Hands up.
Oh, sorry, it's from the last one.
All right. So I can't see any other hands, and I think it's also time to proceed. So thank you again for the presentation.